In this video, we're going to go over just a few more vocab words: electronegative, electronegative difference values, dipole, polar molecules, and nonpolar molecules. And by the end of this video, we should be able to determine if a substance has a charge or a dipole. Remember that thing about like dissolves like? It's based on this idea that charged substances will dissolve with other charged substances, and so on. In a prior practice, we were told whether a substance was charged or uncharged in order to determine if they mix well. What if we're not told if the substance is charged or not? What do we do then? No worries, I can show you how you can tell if a substance is charged if you're not given this information. Okay, we'll break it down by the type of compounds that they are: ionic or covalent. In short, ionic compounds are made of charged ions. I'll give you a short recap on why, and then we'll discuss the other type of compounds, covalent compounds, later. For our ionic compound example, we'll look at NaCl again. Why does table salt have a charge? It starts out with a neutral sodium atom and a neutral chlorine atom. Neutral sodium has 11 protons and 11 electrons. Protons are positive, electrons are negative. Neutral chlorine has 17 positive protons and 17 negative electrons. Here's a Bohr model of a neutral sodium atom and a neutral chlorine atom. At this point, there's no charge at all. Now here's the thing. All elements want to have stable valence electrons. In other words, they want to satisfy the octet rule. So when a neutral sodium atom and a neutral chlorine atom are close together, this happens. The sodium gives away one electron to the chlorine. Now they both have stable valence shells. They have 8 electrons on the outermost energy level. And here's the thing. Sodium has one less electron now, so it has 10 electrons. Chlorine has one more electron now. It has 18 electrons. Since sodium has more protons than electrons, then sodium is now a positive ion. And since the chlorine has more electrons than protons now, then the chlorine is now a negative ion. That's basically how the charges are formed for ionic compounds. Let's just finish this off now. Sodium's outermost energy level from before no longer exists now. So it's technically a smaller ion. Also, positive and negative things, they like to attract each other. So the sodium ion and the chlorine ion come close together. And this is how the compound forms. Okay, why do covalent compounds sometimes have a charge? Like water. Water is a covalent compound. Why does it have a charge? Let's look at an easier example first. Hydrochloric acid. Hydrochloric acid has this Lewis structure. This is where we need to know a few more vocab words. Electronegative. This describes an atom that hogs electrons to itself. Electronegative difference value. This tells you if there is a polarity or a separation of charge between two atoms, and you calculate this number by looking at an electronegativity table, which you can easily Google. And lastly, a dipole moment. This is an arrow that you draw on a molecule that points to an atom that is a lot more electronegative. Okay, with these definitions and this new resource table, we can take a look at why hydrochloric acid is a partially charged molecule. So basically, you need to find electronegativity value for hydrogen and for chlorine for this example. Hydrogen is 2.2. Chlorine is 3.2. Now chlorine is more electronegative here. Now we calculate the electronegativity difference value. So just subtract these two values and get the difference. 3.2 minus 2.2 is 1.0. With this electronegativity difference value, you can compare it to the electronegativity difference chart. Where does electronegativity difference value of 1.0 belong on this chart? Is it a nonpolar covalent bond? Is it a polar covalent bond? Or is it an ionic bond? Well, 1.0 fits right here. It's in the polar covalent section. If you look above where it says polar covalent, it basically means that there's an uneven electron distribution because the more electronegative atom, the chlorine here, is hogging the electrons. This causes one atom to be partially negative and one atom to be partially positive. The atom that is partially negative is the one that is hogging all of the electrons, and you should know that electrons are negative. So if it's hogging all of the electrons, then that atom should be kind of negative, partially negative. So if the bond is polar covalent, we can draw an arrow called a dipole moment. This arrow basically points towards the atom that is more electronegative between the two atoms. Since the chlorine atom is more electronegative, the arrow is pointing towards the chlorine. Since this is a polar covalent bond, we should draw a partial negative charge on the chlorine side, and that will look like this. That means the other atom, the hydrogen, should be partially positive. And this is because there's less electrons hanging around the hydrogen, okay? Because the chlorine was hogging all of the electrons. One important thing that I want you to get from this is that you only really draw these partial negative and partial positives is if the electronegativity values fall under the polar covalent part of the chart. If the electronegativity value falls in the non-polar covalent part, then that means there's no charges around that part of the molecule. All right. I want you to rewind this part again if you didn't follow along, because I know that it's kind of a lot of information here. Okay, if you have a bigger molecule, dipole moments can actually combine together. So you must consider the molecular geometry. We have water here, which is technically a bent geometry, so I have it drawn this way. What's the electronegativity difference value between oxygen and hydrogen here? You need to find the values on the electronegativity table, which is 3.4 and 2.2. The difference between those electronegativity values is 1.2. This means that the bond here is polar covalent. Let's draw a dipole moment to point towards the oxygen, which is the more electronegative atom. It's hogging the electrons away from the hydrogen. Since there's another bond exactly the same right here, then we should do the same thing. But since the electronegativity values are going to be the same, let's just save some time and skip the calculation and draw the dipole moment. Again, point it towards the oxygen since it's the more electronegative atom. It's more electronegative than hydrogen. Here is where we combine the arrows. These arrows will add together to be like this instead, since it's generally pointing towards the oxygen. That means the oxygen side will be partially negative, and the hydrogen side on the other end will be partially positive. That means this molecule has a dipole, which means that it has a positive pole and a negative pole. In other words, this molecule has a partial charge. This is nitrogen trihydride, which has a pyramidal shape. If you calculate the electronegativity difference between nitrogen and hydrogen for this bond, you'll get an electronegativity difference value of 0.8. Now 0.8 will be considered polar covalent again, which means that there will be an uneven electron distribution. You draw the dipole moment arrow pointing towards the more electronegative nitrogen. You also do the same for these two bonds, which will have the exact same electronegativity difference values. So let's just save some time and draw the dipole moments right away and skip the calculation. Now for this example, something interesting happens. There is an arrow pointing left and an arrow pointing right. Since they point completely opposite directions of each other, they cancel each other out. So this leaves us with just the arrow pointing towards the nitrogen, okay, pointing up. This means the molecule will have a partial negative charge near the nitrogen on the top and a partial positive charge towards the bottom of the hydrogen. This molecule has a partial charge. Carbon dioxide molecules have a linear geometry. We have to calculate the electronegativity values for these two bonds. The difference between the electronegativity values for carbon and oxygen is 0.8. An electronegativity difference value of 0.8 means that these bonds are polar covalent. So we have to draw the dipole moment arrows that points towards the more electronegative atoms. For the left bond, the oxygen is hogging the electrons because it is the more electronegative atom. For the right bond, since this involves the same elements, the oxygen is hogging the electrons too on the right side. Now, since the arrows are pointing in the exact opposite directions, this means that they will cancel out. What's really going on is it's kind of like a tug of war for the electrons. Since it's being pulled to the left and to the right by both oxygens with the same amount of force, that means that the electrons are not moving anywhere. They're staying at the same place. This also means that there's an even electron distribution. Okay, it's an even electron distribution throughout this molecule. So that means there is no charge. We have a molecule with a trigonal planar geometry now. So let's calculate the electronegativity difference between aluminum and hydrogen now. It's going to be 0.6, which falls under the polar covalent section. So let's draw the dipole moment arrows that point towards the more electronegative atom for each of these bonds. Hydrogen is going to be the more electronegative atom for each of these bonds, so we should draw an arrow pointing towards the hydrogen for each of these bonds. Now, for this example, since the arrows are pointing in completely opposite directions from each other, guess what's going to happen? They cancel out again, okay? Again, since all of the hydrogens are trying to hog or pull the electrons away from each other with the same amount of force in the completely opposite direction, the electrons don't move anywhere. They stay at the same place. That means that there will be no separation of electrons here, meaning no separation of charge, meaning this molecule is not charged, okay? Last example, and this one's also a trigonal planar molecule. We have to find the electronegativity difference values for these three bonds. Two of them are the same, so let's calculate it once for these two. For carbon-hydrogen bonds, the difference in their electronegativities is 0.4. This makes it so that the bond is nonpolar covalent, which means that there is already an even electron distribution, and we don't even have to draw a dipole moment arrow for any of the carbon-hydrogen bonds. For the carbon-oxygen bond, we calculate the electronegativity difference value, which is going to be 0.8, which means that this bond is polar covalent. So we do draw a dipole moment arrow pointing towards the more electronegative atom in this bond, which would be oxygen. Since there's nothing canceling out here and there's only one dipole moment arrow, there is a separation of charge here with a partial negative charge on the oxygen end and a partial positive charge on the other end, okay, on the kind of carbon side. That means that this molecule is a partially charged molecule. We just need to go over two more vocab words now, which is easy. Polar molecules. are molecules that have a dipole or partial charges, while nonpolar molecules are molecules that don't have any charge. Okay, so I've got a question for you. Look at these same molecules below that we already touched upon. Which one of these molecules are polar molecules? Which ones are nonpolar molecules? I'll give you about 5 seconds to think about this. Okay, here they are. So basically the ones that have charges, the partial charges on them, those are polar molecules. I hope you found this part easy. All right, lastly, I have some practice for you. I want you to use your knowledge about the electronegativity of atoms to identify if a molecule, the molecules below, are polar or nonpolar molecules. And if they are polar molecules, I would like you to identify where the partial positive charge and where the partial negative charge is on that molecule. So pause the video. I want you to try it on your own first before you look over how I did it. Okay, hopefully you tried this on your own. I'm going to go through it one by one this time. For the first molecule, let's see. We're going to have to calculate all of the different electronegativity difference values between all of the bonds here. So there are, let's see, I think there are 3 types of bonds here. The carbon-hydrogen bonds, the carbon-carbon bonds, and the carbon-oxygen bonds. So for the carbon-hydrogen bond, the electronegativity value is 0.4. For the carbon-carbon bond, the electronegativity difference value is 0. And for the carbon-oxygen bond, the electronegativity difference value is 1.2. Out of all of these electronegativity difference values, the only one that is considered polar covalent is the carbon-oxygen one. So that means we draw a dipole moment arrow for the carbon-oxygen bond, and it points towards the oxygen since oxygen is more electronegative. So this also means that there is a partial negative charge on the oxygen and a partial positive charge on the carbon, which makes this molecule a polar molecule. Okay, it has partial charges on it. For the second molecule, we have a small molecule, fluorine gas, and there's only one bond here. It's a fluorine-fluorine bond. The electronegativity difference value between a fluorine and a fluorine is going to be 0. So that means this bond is nonpolar covalent. That means there is no separation of charge, and this molecule is going to be nonpolar. For our third molecule, we have 4 bonds, but they're all the same. There's a carbon-bromine bond. Now, the electronegativity difference value between carbon and bromine is 0.4. And that means that all of these bonds are nonpolar covalent. We don't have any separation of charge for any of these bonds. So that makes the entire molecule nonpolar. Okay, it has no charge. For our last molecule, number 4, we have a lot of different bonds going on here. We have carbon-carbon bonds, carbon-hydrogen bonds, carbon-nitrogen bonds, and nitrogen-hydrogen bonds. So let's take a look at all of these electronegativity difference values. Now, the only one that is considered polar covalent is the one that has an electronegativity difference of 0.8, okay, the nitrogen-hydrogen bond. So only the nitrogen-hydrogen bond will have a separation of charge. And we're going to be drawing a dipole moment arrow for this. So we draw the arrow pointing towards the nitrogen because nitrogen is more electronegative than hydrogen. And that means that there is a partial negative towards the nitrogen and a partial positive on the other side, on the hydrogen side. That makes this molecule, okay, this whole molecule, a polar molecule because there are partial charges on this molecule, right? Now, I know that this can be a little bit challenging, but it's just a matter of breaking it down step by step. I do have a little bit more practice for you so that you can try this on your own, and I'll give you some feedback for those.